This interactive simulation plots the trajectory of a sphere. An important thing to realize, this is for a non-rotating sphere, and rotation can have a significant effect on the distance traveled because it affects the drag. But here we're just looking at a non-rotating sphere, and we're looking at the effect of surface roughness. So the 4 plots shown here correspond each to different surface roughness and actually different launch angle also. Just to demonstrate, we can display multiple ones with different values. The last one we displayed, that's the corresponding drag coefficient. So you notice, as a function of Reynolds number, has this unusual behavior, and the minimum of drag is at a specific Reynolds number. The code for these graphs is the legend on the right side. So the smooth surface, for example, is this trajectory. So you can clear the plot and then start over again. You can change the launch angle and you can change the velocity. And this is a drop-down menu for surface roughness. And then as the simulation takes place, these values are continuously updated. The velocity, the Reynolds number, the drag coefficient, and the drag force. So let's look at the simulation and observe the behaviors we change things. So here's the interactive simulation. If we look at a golf ball and notice the behavior as the Reynolds number increases, drag coefficient decreases. So if we launch this, we notice these values for velocity, etc., are continuously updating. If I change the launch angle and then launch again, notice. So we can increase the velocity and the same launch angle, and of course, not surprisingly, it goes further for the higher velocity. And the simulation updates the position to keep things on the graph. If I switch over to a smooth surface and launch at those same conditions of velocity and angle, notice that ball does not go, the sphere does not travel as far, and here we see the drag is higher until we get above around 4 times 10 to the 5th Reynolds number. So the simulation allows you to pick from different surface roughnesses, which is just the indentation, if you like, which is soon to be uniform little valleys and mountains as a function of the diameter. So the indentation divided by diameter of the sphere. And then the golf ball has unique structure, and we're using data from literature on the behavior of the golf ball.